What happens when the compass of the modern world suddenly stops working? How do billions of dollars of advanced military machinery navigate when the satellites they rely on go dark? For decades, our military dominance has depended on an invisible thread stretching from space to the Earth. But that thread is snapping. The pressing issue today is not about building a bigger bomb, it is about an impossible problem. How do you guide a ship, a drone, or a soldier through contested territory when the enemy can simply erase their location data? The answer lies in the weird, mysterious realm of physics. We are moving from the era of space-based satellites to the age of atomic certainty. Welcome to the invisible revolution. Today, we are exploring the ultimate wonder weapon of logistics and navigation. We are diving deep into quantum navigation systems. To understand the quantum revolution, we must first look at the system it is built to replace. The legacy counterpart is the Global Positioning System. This system relies on a constellation of approximately 31 active satellites operating in medium Earth orbit. Picture the operation flow sequentially in your head. First, these space-based satellites broadcast precise time and location data using specific radio frequencies down to Earth. Next, a physical receiver on the ground must catch these faint signals. Finally, the receiver needs a clear line of sight to trilaterate signals from a minimum of 4 different satellites to pinpoint its exact location. The strengths of this legacy system are immense. It provides ubiquitous global coverage across the entire planet. It supports an unlimited number of simultaneous passive receivers without overwhelming the network. These receivers are highly miniaturized, often scaling down to the size of a tiny microchip. Because of this convenient size, the system is deeply integrated into nearly all modern military logistics, targeting, and command architectures. It boasts decades of proven reliability in permissive environments where the enemy cannot fight back. However, there is a massive dance of conflict between its cost and its vulnerability. A single Block 3 satellite costs roughly $500 million, while the annual operation and maintenance of the constellation drains approximately $1.5 billion. Despite this massive financial investment, the system has a fatal flaw rooted in basic physics. By the time the satellite signal reaches the surface of the Earth, it is extremely low strength. This makes the system physically vulnerable to localized and wide-area radio frequency jamming. It is also susceptible to cryptographic spoofing attacks, where enemies feed fake location data to receivers to misdirect troops or missiles. Furthermore, the system is entirely inoperable underground, deep underwater, or in heavily shielded environments. The satellite constellation itself remains vulnerable to kinetic anti-satellite weapons and severe solar weather events. The old system is breaking down, but a new solution is already locking into place. The next-gen weapon stepping into this vulnerable gap is the quantum navigation system. The architecture of this new technology completely eliminates the need for vulnerable space satellites. Instead of looking up to space, it looks inward at the atomic level. Here is how the structural design and operational flow work. The hardware utilizes cold atom interferometry, which involves measuring the behavior of rubidium or cesium atoms alongside quantum accelerometers and optical clocks. The architecture relies on trapping these atoms inside a sealed vacuum chamber. Then, the system cools these atoms down to near absolute zero using specialized lasers. By measuring the interference patterns of these supercooled atoms, the system can determine precise acceleration and rotation. When we compare this operational flow to the legacy counterpart, the improvements are staggering. Because the quantum system measures its own internal atomic movements, rather than waiting for a faint external signal from a satellite, it operates entirely independently of external networks. This gives the technology absolute immunity to electronic warfare, radio frequency jamming, and spoofing. It is capable of functioning entirely underground, deep underwater, and in highly contested airspace where traditional signals are blocked. Furthermore, it boasts negligible drift rates compared to traditional mechanical navigation systems, meaning it stays highly accurate over long periods without needing to reset its position. However, this new architecture faces severe physical constraints. It currently suffers from immense size, weight, and power limitations. The complex vacuum systems, magnetic shielding, and continuous laser cooling require massive power budgets. Currently, these physical footprints are the size of a massive server rack, or even larger. The hardware is also highly susceptible to environmental shock, vibration, and thermal fluctuations, which can disrupt the delicate atomic measurements and corrupt the navigation data. Despite these hurdles, the research and development investments are scaling into the billions of dollars globally because the strategic value is too high to ignore. This brings us to the most critical question. When will this wonder weapon actually hit the battlefield? These real-world tests provide hard, undeniable data on exactly when this technology will officially hit the battlefield. Defense intelligence and strategic analysts confirm that quantum sensing is much closer to deployment than most other advanced technology projects. The exact future deployment timelines officially indicate that military-grade quantum navigation systems will begin scaling across allied defense forces within the next 12 to 36 months. Official defense contracts specifically target fielding operational quantum inertial navigation units by 2027 or 2028. Following the aggressive military rollout, widespread commercial aviation integration is estimated for 2029 and beyond, once regulatory agencies establish strict certification pathways for these internal atomic sensors. The strategic impact is profound and immediate. The decades-long era of complete global satellite dependence is rapidly ending. The immediate future of advanced military navigation will be guided entirely by the absolute precision of supercooled atoms operating in complete isolation. The transition from a laboratory experiment to a battlefield reality is already happening today. In 2022, researchers at Imperial College London, working in collaboration with the United Kingdom Ministry of Defense, successfully tested a standalone commercially viable quantum accelerometer. This represented a foundational milestone for absolute navigation on naval vessels without relying on traditional external satellites. The next major breakthrough came when engineers at Sandia National Laboratories built a compact, passively pumped vacuum chamber specifically designed for cold atom sensors. This crucial engineering achievement significantly reduced the immense physical footprint and power requirements of the technology, allowing it to transition from massive static laboratory tables directly to mobile tactical platforms. Since those foundational milestones, the pace of testing has accelerated directly into real military environments. By the summer of 2025, advanced defense companies successfully deployed a quantum dual gravimeter on a Royal Australian Navy training vessel. During this rigorous maritime trial, the quantum system operated continuously for over 144 hours. It successfully collected precision navigation data with zero human intervention while actively operating at sea. Around the exact same time, the United States Air Force launched the X-37B spaceplane, carrying specialized quantum inertial sensors for rigorous orbital testing. This specific test validated the capability of quantum sensors to operate flawlessly in the harsh environment of space, where alternative navigation signals are completely unavailable. None of this revolutionary technology would be possible without the relentless grit and brilliant problem-solving of the global engineering teams behind these quantum systems. Dedicated physicists and mechanical engineers have spent decades fighting against the brutal realities of thermal dynamics and complex atomic instability. They took an impossible concept that once required an entire room full of delicate lasers and compressed it into rugged tactical hardware capable of surviving the violent shockwaves of a deployed naval warship. Their immense contribution is actively rewriting the future of global defense strategy. They are successfully solving the most complex logistical problems of modern warfare, one single atom at a time. Now we want to hear exactly what you think about these developments. Which next-generation military technology should we thoroughly investigate and break down next? Do you want to see a technical deep dive on high-end near-peer capabilities like hypersonic munitions? Or perhaps a tactical analysis of advanced autonomous platforms? Drop your preference in the comments section below. If you found this rigorous engineering first breakdown valuable, make sure to hit the like button and subscribe to the channel right now. Your direct support helps us grow and allows us to continue bringing you the absolute best factual analysis of the most advanced military technology on the planet.